So we spent most of last week developing a way of solving systems of linear equations, and we introduced a lot of new concepts. So I think it's helpful to just have a lecture where we recap the basics of exactly what we did. So we're going to do most of our examples using two equations and two unknowns, but remember we can have as many equations and as many variables as we want. So if we have two linear equations, and remember a linear equation means that whichever variables you have only appear as themselves. They're not raised to any powers, they're not multiplying each other together, and they just have numbers as coefficients. So that's a linear equation. And if we have two linear equations, so we have two equations for straight lines, then there are three possible solutions when we try and solve these two equations simultaneously. One option is that we get a single point of intersection for our two lines. And this means that our solution set contains just that point. On the other hand, it could be that our two lines are parallel. And in this case, if we're looking at these equations over here, this means that our coefficients of our x term are the same, but our constant terms are not. So this is two lines that are parallel. And in this case, our solution set is empty. There are no points which both lines go through. So we have no solution. And then finally, we can have the odd situation where, in fact, our lines lie on top of each other. So lines are the same. And in this case, our solution set is an infinite set. And we have infinitely many solutions. And although we've taken this very simple situation where we've got two equations and two unknowns, it turns out that no matter how many linear equations in unknowns we have, we only have three possibilities for the solution set. A single point of intersection, no points of intersection, or infinitely many. So this is why it's useful to work with two equations and two unknowns, because it covers many of the situations that we would see in more complicated things. So we know from work that we did in Matrix is to solve simultaneously means you take your two equations and you do stuff. Maybe you substitute for y in terms of x, and you want to end up with a new system of equations which look much simpler and give you the answer. So you might never have really thought of your answer as a set of equations, but this is a system of equations. It says x is equal to 4 and y is equal to 0. Now we know that we can add multiples of one equation to get our two equations into the solution form. So we looked at that and then said, well, it gets tedious working with the equations. It would be useful if we had a kind of shorter method. And so we introduced the idea of an augmented matrix. We know that a matrix is a rectangular array of numbers, and our augmented matrix is the matrix whose rows are the coefficient rows of the equations. So you can go and revise all the terminology, but the way we get the augmented matrix for this system of equations is we look at the coefficients of each of the variables. We draw a line which kind of matches where the equals sign is in the equation, and then we put the constant term on the other side. And it is this augmented matrix that we're going to use to solve for the solution for the system of linear equations. So Gauss reduction, which we also called finding the reduced row echelon form, is a quick standardized way of solving our systems using the augmented matrix. So remember, there are three things that we said we could do in a slightly different order here. We said that we could switch two rows, we could replace a row with a multiple of itself, so long as that multiple is not 0, and then finally we could replace a row by multiplying that row by something and adding or subtracting a multiple of another row. And again, those multiples mustn't be equal to 0. And the method, which I'm summarizing here, is basically the idea: you get a left in the top left corner, you get zeros in the column below it, then you move on to the second column, and in row 2, column 2, you get a 1, make sure that you get zeros above and below it, and keep going until ideally you have 1s on the diagonal of the matrix and zeros below it. So this is the basic method. As we saw last week, it doesn't always work. We kind of have to deal with cases where we get rows of zeros and things, but this is the basic idea. So let's take a moment to just work through some examples. So what I'd like you to do is just take a moment and sketch the following equations on the same set of axes. So what you should have ended up with is something that looks pretty much like this. So here we've got our function f, and here's our function g. So f is actually lying underneath the green one, which is labeled I. G is this purple one over here. H is this blue line here, which runs parallel to both F and I. And as I've said, I is also lying on the, well, I is the green line, and underneath it is F. So we're going to use these four equations to look at the different things that can happen with Gauss reduction for our three types of solution sets. So we're going to look for the first bit, we're going to look at these two, and if we look at the image that we have over here, it seems like they intersect at one particular point. So let's Gauss reduce these and see what happens. So we set up the augmented matrix. And the very first thing we want to do is turn the top left bit into a 1. So we might as well just divide the top row by 2. So we're going to say a half times row 1, which will give us 1, 3 over 2, 6, and 5, 9, 35. So now we've got this 1, we need to make sure that everything else in this column is zeros. Well, the only thing we need to worry about is that 5. So let's subtract off 5 times row 1 from row 2. So we've got row 2 minus 5 row 1. So row 1 is not changing. Row 2 becomes 0, 9 minus 15 over 2, which we'll find is 3 over 2, and 35 minus 30, which gives us 5. So now we've finished with our first column, and we need to find our second column. We need to turn this 3 over 2 into a 1. So let's just multiply through by 2/3. So not changing row 1. 0 times 2/3 is 0. 3 over 2 times 2 over 3 is 1. And we get 10/3 for our constant. So we're almost done. We now just need to finish up and get a 0 over here, which we do by subtracting 3 over 2 times row 2 from row 1. And if we do that, we get 1, 0, 0, 1, and 1 and 10/3. So if we turn this back into a system of equations, what we get is x is equal to 1 and y is equal to 10/3. If we'd originally used, for example, x1 and x2, then down here we'd have x1 and x2. So as we said last week, it really doesn't matter what you call your variables. When working in 2 or 3 dimensions, it's usually we use xy or xy and z, but when you go to 4 or more variables, using subscripts just makes life a little bit easier. So what does this look like? Well, if we go back to our image of our lines that we sketched, the 2 lines that we were finding simultaneously were F. Let's make this a bit bigger. So the 2 lines we were interested in were F and G. And what we claim is that they intersect at this point over here. And if you have a look, if you were to come down to the axis, you'd see that this is the point x is equal to 1, and moving over here, you can see this is the point 10 over 3, which is 3 1/3. So when we find a single point as a solution, we're thinking of 2 lines intersecting. If you're in 3 dimensions, then you'd have 3 planes intersecting at a single point. So that's what this sort of solution looks like. So now let's use the same first equation, but instead we're going to use 6x plus 9y equals 35 as our second equation. So let's go ahead and Gauss reduce. So we've got an augmented matrix that looks like this. Same first step, we want to divide the top row by 1 and by 2. So this is exactly the same as we had before, not changing our second row at all. Now we need to turn the 6 into a 0, so we're going to subtract off. I'm going to say row 2 minus 6 times row 1. So we're not changing row 1. And we're going to get a 0, 9 minus 3 times 3, which is 9. So that's going to give us a 0. And 35 minus 36, which is going to give us a minus 1. And remember, if we think about what equations this augmented matrix represents, it represents the equations x plus 3 over 2y is equal to 6, which is fine. But then it also represents the equation 0 is equal to minus 1, which is not fine. This is impossible. So this means we have no solution. What does this mean visually? Well, let's go back to our set of lines that we sketched. So now we're looking at the line F, which is this green line over here, and we're looking at the line H, which is this blue line over here, and you'll see that those two lines are parallel. So they never intersect, and that's why we have no solution. So the final type of intersection we can have is infinitely many points of solution, and let's see how that looks. So we've got 2, 3, 6, 9, 12 and 36. So we're working with the same equation that we started with, and this looks very much like the one we just found no solution, except we had 35 and this is 36, and it's going to turn out to make all the difference. So usual first step, divide through by 2 to get our first one in the top left. Not doing anything to the second row. Now again we're working to get rid of the 6, so let's say row 2 minus 6 row 1, so we don't change the top row, and what we get is a 0, 0, 0. And what this is saying is we have one equation which says x plus 3 over 2y is equal to 6, and 0 is equal to 0 for our second equation. And this is always true. So in fact, the only thing that we have to satisfy is finding values of x and y that fit into this equation over here. So our solution here, we could say, is just the line x plus 3 over 2y is equal to 6. But we actually learnt a different way of writing this. We said, well, the point about having just this equation for our solution set means that for every single y that you pick, you can find an x that makes this equation true. So we said y is a free variable, and we said let's call it, for example, a, where a is any real number, and then our two equations become x is equal to minus 3 over 2a plus 6, and y is equal to just a. And so in this case we can write our solution set as being the set of all vectors of the form minus 3 over 2a plus 6 and a, where a is in real numbers. What does this look like? Well, again, let's bring up our photo. So now we're looking at f, which I said earlier is actually lying underneath the green line because these are the same line. So this is f and I. So we're looking at these two equations. And the equation of this line that they both lie on is this equation over here. So we're just writing in a slightly different way. When we write our solution set like this, we're basically saying each of these points over here has the form minus 3 over 2a plus 6a for some a in real numbers. So there we've seen, just using two equations and two unknowns, how the three possible solution sets arise. So our summary looks like this. If we end up having finished our Gauss reduction with a reduced row echelon form that has a diagonal of 1s and everything else is 0, so these big zeros represent zeros everywhere, then we have a unique solution which which will be something of the form x1 is equal to a, x2 is equal to some b, and you keep going, you get xn is equal to some c. And that's a unique solution. So it looks like you've got lots of solutions, but this whole point is the solution. On the other hand, if you construct your row echelon form and you find that you've got at any point a row of zeros up to the line representing equals followed by something non-zero. So the important thing here is that this d is not equal to 0. As soon as you get this, you can say no solution. And the final case that you can have looks a little bit like the no solution one, but it turns out to be very different, because here you have a row of zeros before the line representing equals, and you have a 0 afterwards. And this generally means that you have infinitely many solutions, but you need to be a little bit careful, because you need to see how many equations you have and how many unknowns. So it might be, if you had more equations than you have unknowns, then this row of zeros wouldn't mean that you have infinitely many solutions, because you might have, without the row of zeros, the same number of rows and solutions, in which case you might have a unique solution. On the other hand, if you have fewer equations than variables, and you get this row of zeros, then you're going to have infinitely many solutions. So you need to be a little careful here. This could mean, and it usually does, but could also be a unique solution. Having said this, obviously if above that you got a row that had zeros and some constant non-zero, then you definitely have no solution. So if ever you have a row with all zeros except for the last entry, which is non-zero, then it's no solution, regardless of whether or not you have a row of zeros as well. So what I recommend is that you take some time to work through the exercises at the end of section 6.3. They pretty much all give you solutions, and practicing Gauss reduction in a variety of contexts is very important. Just a note, the textbook doesn't put a line between the coefficient matrix and the constant vector in our augmented matrix, but I recommend that you do when you do your own working. Otherwise you can kind of forget what's going on with the Gauss reduction. So you'll notice that we don't have a lecture 8.2, and that's because I'm well aware that Gauss reduction takes a lot of time. So please spend tomorrow working through some more Gauss reduction.